All right, we're going to talk about ideas such as counting, permutations, and combinations. This is a little bit different than grade school counting on your finger type ideas. When we say counting, we're really talking about how many different ways can a particular event occur. One example would be if I have four letters, A, B, C, and D, how many different three-letter codes could I have? And so one option is to just start counting, just be creative and come up with your list. So if I have four letters, I and I'm just going to brainstorm some ideas here. I could do A, B, C. I could do B, C, D. I could do A, B, B, D. And so on and so forth. And one concern that shows up is how do you know you got them all? So we're going to try to show sort of a different way to do that. But that is an option, is to make a list of every possible scenario and go from there. Okay, so we'll revisit that topic. Another example would be you've got a psychologist who's using food as a reward, and there's two rewards with three different varieties. How many different meals can you reward the animal with given three choices and you want any two of them? Well, another idea, instead of just listing out the possibilities, is to do a tree diagram. Tree diagram kind of helps clean up the that you might not have thought of everything. So in this case, you could see that you have A, B, A, C, B, A, B, C, C, A, C, B. And then you just go to the end and count the branches. So 1, 2, 3, 4, 5, 6 options. Okay, so again, this is, you can list it out, you can draw a tree diagram, or there's another concept called the fundamental counting principle. And that is in any situation where you can break it up into stages, and at every stage you have a different decision that you can make, you can apply this counting principle. So if I have S number of stages, and there's only so many ways I could do that, then at each stage I could just multiply. I have, this many options at stage 1 times this many options at stage 2 times all the way till I get run out of stages. So going back through that food experiment problem, my first, I've got three different food choices and I'm giving two different rewards, so there's two stages. The first stage I have three options. During the second stage, I've already given one of the food options, so that's where I get the 2 from, and then 3 times 2 gives us the same 6. That we had when we did the tree diagram. Okay, permutations. So permutations is when we are looking at a group of selected elements and we want a certain combination of them at a time. So an R permutation of set n elements is an ordered selection of R elements from set n. That sounds terrible. We're going to look at some examples of this. Okay, going back to this, I have four letters, and I want three-letter combinations. So of the four letters, I want to know how many total combinations there are. And with a permutation, its ABC is viewed differently than CBA. Same letters, but a different order. The different order gives us a new combination. Okay. Now let me show you in the calculator a couple of buttons that would help figure this out. Let me go back to here. Okay, so in your calculator, one place we want to know about before we get too far in depth here is the permutation button. So if you go if you hit math and go all the way over to probability, you'll see a couple of buttons that are going to come up in a second. So you've got permutation, eventually we'll do a combination, and we just looked at something called a factorial. And so let me kind of show you how each of these buttons work. So if I want to do 5 factorial, so 5 factorial means 5 times 4 times 3 times 2 times 1. Then I'd hit 5 first, do math, arrow over to probability, and then select it, and it does the math for me. In our particular problem, we are doing 4 objects, 3 at a time. So I want a permutation of that. So the way we calculate that is, I believe we start with 4 objects. Then I tell the calculator I want you to do a permutation. And then I want 3 after the fact. And it will calculate that for us. Which means there's 24 different combinations that one could come up with. Okay. Combinations is another calculator button that I showed you a second ago. It works the same way. In combinations, we're looking at, similar to permutations, we're looking at so many objects, but I want to look at a smaller grouping within them. And in this case, order doesn't matter. In other words, A, B, and C and C, B, A are viewed as the same thing. Okay. An idea that gets associated with that is committees. So if I have a committee of 4 people and I want to pick 3 at a time, okay, does it matter which order people were picked? So if I pick you first or I pick you last, you're still on the committee. Everyone's got the same authority, in which case order doesn't matter. So this would be a combination. And we type that in for combination 3. Kind of make sure we understand that in the calculator. So if I do 4 and then arrow over to combination 3, I get 4 objects. So there's 4 different ways that I could rearrange these if the order doesn't matter. Okay. One nice analogy that I like to bring up when we talk about permutations and combinations. Permutations, think of it like they're presidents. If I pick you first, you're president. If I pick you second, you're vice president. If I pick you third, you're secretary. So if I'm drawing names out of a hat, order would matter because whoever's first gets to be president, gets to call the shots. Whereas combinations are more like a committee. In combinations, it doesn't matter because whether you're picked first or last, you have the same authority. Okay. All right, so let me keep going here with these examples. All right, how many different ways can the 4 letters of a radio station be arranged if the first letter must be W or K and no letters repeat? Okay, so we have to kind of think for a second, what type of problem are we looking at here? Does this sound more like a counting problem, a combination problem, or a permutation problem? Or maybe it's a hybrid, maybe it's a both, more than one option. Can we break this up into stages? So for example, I know there's 4 letters, but I know there's only 2 choices for the first letter. So this would be more of a counting principle idea. So we've got 2 options to the first one. Since I've already used the letter up, the second one can only have 25. The third one, we're down to 24, and the fourth one down to 23. So just type that in the calculator and we have 27,600 choices. How many ways can our class elect a president, vice president, secretary if no one can hold more than one office? So we have to kind of know how many students we're talking about here, but in this case we're talking about a permutation. Order matters. Whoever gets picked first is going to be, have more authority than others. How many 5-card hands are possible from a standard deck of cards? Okay, so this is kind of a fun one to think about. Since when you're looking at a deck of cards, the order doesn't matter, whether you get the ace first or the ace last, you still have an ace. That would be more an example of a combination. So there's 52 cards in a deck, combination of 5 at a time. So 52 combination 5. Given digits 5, 3, 6, 7, 8, and 9, how many 3 digits can be made if the first digit must be prime? And the digits, I'm sorry, can digits be repeated? That's a question. All right, so let's think about if it's got to be prime, how many choices are there for the first one? How many prime numbers are there? Well, we got 5, 3, and 7 are the only prime numbers, so there's 3 options there. If we allow repeating, is that going to change the numbers? Okay, and the answer is, well, after we've used a number, we can't use it again. Okay, so let's talk about what happened, why this order. So because they said prime, that means the first number's got to be 3, and then the second number of the 6 digits, we've only got 5 left to pick from, and then the third choice, we've already used 2 digits up, so there's 4 left. Okay, how many ways can 9 horses place first, second, and third in a race? Okay, is this a stage thing, or is this a combination permutation thing? And we're looking at a combination of permutation. And does order matter? If you come in first, is that going to be much better than coming in third? And yeah, that is. So we're looking at a permutation of how many things? Well, there's first, second, third, so we got 3 places, 9 total. So it's a permutation of 9 comma 3, 9 objects, 3 at a time. Okay, suppose we have 15 girls and 18 boys. How many ways can 2 girls and 2 boys be selected? This is the first time we're going to look at a hybrid of counting principle and combination permutation. Counting principle meaning we're going to take the number of options for girls and times it by the number of options for boys. And so since there are 15 girls in the class and I want any 2 of them, that first set gives me the total number for girls, and since I want 18 boys 2 at a time, that second set gives me the number of boys.